Rademacher complexity is another complexity measure that can assess the complexity of our hypothesis class. In other words, when the Rademacher complexity value is high, which means our hypothesis set or our function class is very complicated or has many freedom to control or many runnable parameters. So we can very flexibly control our running process, and we can fit any type of training data point, which is very nice thing. But on the other hand, because of such high complexity, we can suffer from the overfitting issue, the high generalization gap, which means the training error and the test error can differ significantly. In this lecture, in this week, we will discuss Rademacher complexity, which will give you another view of complexity compared to VC dimension. Okay, so let's review the representative property. So to simplify our notation, let's denote the function class f, which is cascade function of hypothesis and the loss function, which means there are inputs. So z represent input and the label pair, x and y pair, which is z. So that is kind of one single training data point or test data point. The data point go to our hypothesis. So x go to our hypothesis, and hypothesis make some prediction. And the loss function measure the difference between the hypothesis and the true label y. Okay, so the loss function usually a function of hypothesis and the training data point. So for each hypothesis, we can define a function with respect to training data point. That is the f function class. So for the f function class, we can define representativeness as follows. Let S, the set S, be a training set which randomly sampled from distribution D. So there is given data generation distribution D, and at each time we randomly generate one single data point from this distribution D. So if we want to make M training data point, we simply repeat the same random sampling process. So the training data set S consists of IID random samples comes from distribution D. And the representativeness of the training data point S with respect to the function class f is defined as follows. So this is the notation of representativeness with respect to the data generation probability D or distribution D. For the function class f and for the training data sample S, that is supremum of LDF minus LSF. So this is training error. This is test error. So expected error with respect to the data generation probability or process, minus this is the training error for given M training data point, the empirical loss value. So we want to compute the supremum. Supremum means the worst case of this generalization gap, the test error minus the training error, test loss minus training loss among whole our function class. So in general, the training error is smaller than the test error because we fit our function with respect to the training data point. We usually fit more accurately to the training data point. So the test error usually higher than the training error, but that is for the case f comes from the ERM rule, empirical risk minimization. And in some cases, the test error can be less than the training error. In some extreme cases, the training error can be very, very high, although the test error is very, very low. But for the empirical risk minimization, our trained function f has small training error compared to the test error because we find the best fitting model for the training data samples, right? So we are interested in the difference between the test error and training error. So test error minus the training error. And the representativeness is defined as follows. So which means the meaning of representativeness, we want to find out the extreme case, the extreme case that has the largest generalization gap, the difference between the test error and the training error. Okay. So the representativeness, we can approximate the representativeness using the training set and validation set. So for the cross-validation, when we find the right model to train to fit our training data point, we usually use cross-validation. We usually split our training data point into two different parts, two disjoint parts. One is training data set and one is validation data set, and we find a good model that explain the training data very well using training data point, and then estimate the true performance of the trained model using validation set, which is called validation error. So in previous case, the test error, the true test error can be estimated using the validation set, the validation error, and the test error, the training error can be estimated using the training set. So when we have original training data point, training data set, we usually split the training data point into two different parts, S1 and S2. So think S1 as the validation set and think S2 as the training set, then the empirical loss comes from the S1 is considered as the test error, so which is approximation of the test error, and the empirical loss with respect to S2 is kind of training error. So we want to find out the supremum of LS1F minus LS2F, which approximate the representativeness. So which approximate the test error minus training error. Okay, so let's change the order. Okay. So random split defined by a random vector. So we can define this split S1 and S2 using the sigma vector. So what is the sigma vector? So sigma vector is a random vector in the -1 and +1 m-dimensional vector. So sigma is m-dimensional vector, so it has m element, and each element is either -1 or +1. And then S1, the first set, can be considered as the whole element index, which has the positive value. S2 as the whole trained data point corresponding to the element having -1 value. So basically we have data points Z1 to Zn, And when we randomly sample sigma from this set, each element of sigma will have either +1 or -1 with probability of I did not define the distribution yet. Anyway, you can define S1 and S2 using the value of each index of each element. Okay, then if we further assume that the cardinality of S1 and cardinality of S2 are the same, then from the definition of this, we can say that the LS1F minus LS2F is equal to 2 over M times summation I1 to M sigma I FGI. Then which naturally make 2 over M, this is the cardinality of set 1 and cardinality of set 2, times summation of FGI, where I belong to the set 1, so GI belong to set 1, minus 2 over M summation GI belong to set 2 FGI. So this is the empirical loss with respect to set 1, and this is the empirical loss with respect to set 2, which is exactly the definition of approximate representativeness. Okay, so using this sigma vector, -1 + 1 vector, we can express the approximate representativeness from the original training set S. So extending this, we more generally define the approximate representativeness, that is Rademacher complexity. Let the variables in sigma be distributed IID according to this uniform distribution. In other words, the probability sigma I is equal to 1 is the same with the probability sigma I equal to -1. They both are the same with 1 over 2. With this random vector sigma, the Rademacher complexity of our function class F with respect to the dataset S is defined as follows, with basically the approximate representativeness. Okay, so this is 1 over M times expectation with respect to the sigma, random sigma that belong to 1 minus 1 m-dimensional vector, and each element randomly sampled independently with distribution 1/2 coin tossing. So value 1 with probability 1 over 2, value -1 with probability 1 over 2. And with this random variable, for each random variable, we find extreme case. So remember, so note that here we do not fix a function class, but we control the function for each randomly generated sigma vector. So for each randomly generated sigma vector, we find the supremum, the extreme case of function in our function class that maximize the difference between estimated test error or validation error minus the training error. When we randomly generate the validation and a test set using sigma vector minus plus m-dimensional vector. Okay, then when in some cases the sigma vector can have very small validation and training gap. In some cases, the sigma vector can make very large generalization gap between the validation and test error. But in the Rademacher complexity definition, compute the expectation with respect to whole the sigma random vector. Okay. So more generally, the Rademacher complexity is this: for any given set of vectors A, member of m-dimensional vector A is equal to 1 over m times its expectation over sigma, random sigma vector, which comes from a uniform distribution over 1 minus 1 m-dimensional vector field, vector space. Supremum A, so this is kind of function class. Summation I1 to m sigma I times ai. Okay, so that is Rademacher complexity. And intuitively, the Rademacher complexity can explain the generalization gap of our function class or our hypothesis class, because when this R value is very small, which means for any extreme case, even for the extreme case, the validation error and the training error almost the same. So when this Rademacher complexity, we do not worry about the high generalization gap, because even for the extreme case, we have very small generalization gap between validation and training error. Okay. In other words, when Rademacher complexity is very high, huge, then we should be careful for the high generalization gap. In some cases, our training data samples can be difficult to make a good algorithm, because in some cases our training data and validation data has high differences. So when we train our algorithm or our hypothesis only using training data point, that could make high test error. So Rademacher complexity is not always can give you very nice indicator for the generalization gap, because we are considering extreme case. Generally, we do not go to the extreme case. So Rademacher complexity not always give you very accurate indicator for the generalization gap, but at least we can say that when the Rademacher complexity is very low, we don't worry about the generalization behavior. We can clearly say that well-trained model can perform very well for the randomly generated new data set or the test error. But for high Rademacher complexity case, we maybe need to check the validation and training gap, because in that case there is some cases your training data can be extremely biased to some subset of your hypothesis, so that the generalization gap is very high. Okay.